Write down the Maclaurin series of e to the x in ascending powers of x up to and including x cubed. Right, I'm going to remind you at the end of this video about where this actually comes from, but we are given it in the formula book, so we're just going to focus on applying it. We can expand a function in terms of, it's like a power series in increasing powers of x, but we're relating the derivative each time. So we've got f of x equal to e to the x, and then f of 0 would just be e to the 0, it would be 1. But the thing about this series is that every single time the derivative is going to be e to the x. You could do triple dashes for this one. Sometimes people use a little 3 to indicate that we're doing it 3 times. But all of these then are then going to be 1. Which means e to the x is going to equal 1 plus x times f dash 0, that's just x, plus x squared over 2 factorial times 1, so x squared over 2, plus x cubed over 3 factorial times f dash 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 0, that's going to be x cubed over 6. And that is our Maclaurin series, up to including x to the 3. Then we're asked, without differentiating, to determine the Maclaurin series of e to the x minus 1. There's actually a lot of different ways to do this, but probably the simplest is to use our answer from part A and substitute straight in for the e to the x. So I'm going to get e to the 1 plus x squared over 2 plus x cubed over 6, and then I'm minusing 1. I'm going to cancel these out. And now I'm going to apply this formula, but with x replaced by this term here. Other ways you could do it is you could write it as e to the x times e to the x squared over 2 times the other one, and then do Maclaurin series in terms of them. But that would be like a product of 3 functions. I don't think that is actually going to be any easier. You could actually expand the original series, but replace this by e to the x minus 1, and then at a later point get it back in terms of x. But this is the best way. So I'm going to get 1 plus x squared over 2 plus x cubed over 6. So I've dealt with that term and that term. Then I'm going to be plussing. Okay, now I'm going to get the same thing, but it's x plus x squared over 2 plus x cubed over 6. And then I'm squaring that and dividing by 2. And then finally, one more term, x plus x squared over 2 plus x cubed over 6 cubed over 6. Now remember, we're only interested in expanding up to x to the 3, so it's not like I actually have to work out every single one of these. So maybe I'll do it one at a time. I'll call this one star and this one double star. Then we'll bring it back together. Then we write a little bit less. So star is going to be x plus x squared over 2 plus x cubed over 6 multiplied by itself. Don't forget we're dividing the whole thing through by 2. Now remember, we're only interested in the terms up to x cubed, so I can ignore the rest. I'm going to get x times x to give me x squared, then x times x squared over 2 to give me x cubed over 2. But if I do the next one along, I'll get an x to the 4 term, so I can ignore it. So I can now go to this term times this. That'll give me another x cubed over 2, so I can just double. And then that's it. That's all I need. Don't forget, and then divide them by 2. So I will get x squared over 2, these cancel, plus x cubed over 2. Let's take a look at double star. Now the only way I'm going to get an x cubed term here is if I times x by itself each time in the brackets, and then that's it. Well, then I'll just be dividing by 6. because when you think about it, I'll just have the same thing. That will be a 6, and then I'll get another bracket here. So it'll be that times that times that. If I include anything else, then I'm going to get a higher power. So I don't need to write the whole thing out. I can just write that as x cubed over 6. And therefore, e to the x minus 1 is going to equal 1 plus x squared over 2 plus x cubed over 6. And I've got my star, which is x squared over 2 plus x cubed over 2. Let me just highlight that. So that is star, and then my final double star term, which is plus x cubed over 6, plus higher powers, of course. 1 plus x, dealt with those. Then I've got x squared over 2, another x squared over 2, that gives me x squared. Oh, so I'm just going to get x squared here. And then x cubed over 6 plus x cubed over 6, that's x cubed. Actually, let's put it all over a common denominator. So this one here would become 3x squared over 6, which means I'm going to get 5x cubed over 6, 5 over 6, x cubed. That is my answer for the Maclaurin series of e to the x minus 1. Now, I did say I was going to show you where the formula comes from. Just going to remind you, it's really interesting. So let's say we've got a function. We're trying to write it as a power series. Then it would be a plus bx plus cx squared plus dx cubed, and so on. I'll add some more terms if I need to. But what we could do is we could substitute 0 in, because this has got to be valid for all values of x. We could do f of 0 equals a. And then that means I can replace this by f of 0 in a minute. Now let's find the derivative. Then I'm going to get b plus 2cx plus 3dx squared, etc. Now let's find out f dash 0. So that is going to equal just b, because all the other terms disappear. And we just keep going. Next up, I'm going to get 2c plus, it's going to become 3 times 2. I could even write that as 3 factorial dx. So f double dash 0 is going to equal 2c, which means c is going to be this divided by 2. And then we'll do one more. So the third derivative is going to be 3 factorial d plus some other terms. So here we're going to get 3 factorial d by itself because the other terms are going to disappear, which means d is going to be f. And from that, we can construct our f of x. It was a, which we've just showed was f of 0, plus bx, that's our f dash 0x, plus cx squared, so that's f double dash 0 over 2 x squared, and then f3 of 0, sorry, over 3 factorial multiplied by x cubed. And then it will just continue that way. I haven't, so it's not like a foolproof or anything, but it's enough motivation just to remind you where that comes from. Well done.